Hi, everyone. So today what we're doing is we're talking about limits once again. In the last couple of lessons that we've been working on, I actually gave you the graph. And when we look at the graph, we can say what that looks like. Now today, I'm going to give you guys equations, and we're going to be able to figure out what the limits are for these equations. So no graphing necessary. And this is something that we're going to take to us in calculus because we're going to see a problem and we're like, man, what would that limit be? That limit looks really hard, but it's actually pretty simple because mainly we're going to look at these right now, limits as x gets closer to infinity, and we're going to give ourselves a fraction. Okay, a fraction. And this fraction we also can call a rational functions. Now, let me give you a simple example of this. And this is an example of the limit as x approaches infinity of 1 over x. Okay. Now, what am I trying to describe here? When we said limits, I had a slogan for limits. Let's see if you guys can remember what my slogan for limits. Limits are what something is or what something should look like. And the way I like describing limits in a very layman's term is what should it look like? What is, not what is it, what should it have been? Okay. Now, looking at the graph here, as I plug in x values, okay, x, if I plug in 1 over 1, oh darn, that's ugly. If I plug in 1 over 1, right, 1 over 1, that's 1. How about 1 over 2? That gets smaller. 1 over 3, getting smaller. 1 over 4, getting even smaller than that. And you can see as x gets bigger, doesn't this number get smaller? Let's go ahead and show that. But what if x gets smaller? What do I mean by smaller? Not more negative, but what if I wrote x is 0.5? What if x is 0.25? What if x is 0.10? So where are these numbers located? Well, 0.5 is right here. 0.25 is half of that, and 0.1 is even closer. So as x gets closer to 0, this number shoots up. How many 50 cents? How many 50 cents are in a dollar? 2. How many quarters are in a dollar? 4. How many dimes are in a dollar? 10. And this graph ends up shooting up this way. Okay. On my left side, all the numbers are just 1 over -1, 1 over -2, 1 over -3. 1 over 1 is 1, 1 over 2 is 0.5, 1 over 3 is 0.333, but it's all the same numbers on the right except negative. So the graph actually looks like this. And as we head towards 0, it actually shoots up to infinity. So this is our graph of 1 over x, and we've seen it before. This is not new. We also have a vertical asymptote at x equals to 0, because if I plug in 0, we end up dividing by 0, and we mentioned when you divide by 0, it's undefined because it shoots off to infinity. And you can see the graph shooting off to infinity. Now, we described what the graph looks like as it heads toward infinity. I wonder if you guys remember this. We actually had a rule here. What would the graph look like as x went to infinity? And we said that if the bottom is bigger, this would go off to 0. Now this heads back to our 3 rules. Let's look at our 3 rules for rationals. And we said if the fraction x to the a over x to the b, okay, plus blah, 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 dot, 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 plus blah, dot, dot, dot. We said that if rule 1, if b is bigger than a, if the bottom has a larger exponent. Do you guys remember what happens to the graph? What is my horizontal asymptote? Do you guys remember that? If the bottom exponent was bigger, does anybody remember what the horizontal asymptote would have been? If I write 1 over x squared, x plus 1 over x squared. What if I write x squared plus 3 over x to the 4th plus 1? Okay. If the bottom is bigger, we said the graph is eventually going to become 0. Now, I'm not sure you guys remember the logic behind that. If I tell you the number on the bottom is a larger exponent, as x gets bigger, 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 who's going to be running the race faster, an x squared or x to the 4th, an x or an x squared? The bottom fraction, the bottom denominator, we said, if it has a bigger exponent, it's going to be running faster. And that buries the top. And when a number on the bottom buries the top, 1 over 4, 1 over 5, 1 over 10, 1 over 100, does that number get bigger or smaller? The number smaller and gets closer to 0. And that's exactly what happens here. What has a bigger exponent, the 1 on top or the x on the bottom? The x on the bottom has a larger exponent, so as x gets larger, it buries the top, and we get buried to 0. And that's actually what our first goal is. Our first goal is to just look at the fraction and say, hey, what does the graph do if we could go to the right to infinity? And as I plug in numbers, 1 over 10, 1 over 100, 1 over 1,000, that 1,000 buries the 1 on top of it, and it gets closer to 0. It becomes such a small number. 1 over 1,000 is a very small number. It pretty much, so what does it look like? At infinity, it looks like 0. So our answer here, let's go back and rewrite it. The limit as x approaches 0, sorry, infinity of 1 over x is equal to 0. Okay, equals to 0. And that's really our first steps here. This is our first rule, but this rule is not really even a new idea. We've been talking about rationals for the last 2 months. We talked about it before, and we were like, what happens to this graph as x gets larger? Well, in this case, it goes to 0. Okay. So what about this other fraction if I give it to you? What is the limit as x goes to infinity of 2x squared over 3x squared plus 4? So this is another problem that we've seen before. I could ask you to graph it. We could graph this, okay? But I actually want to just use the rule. Do you guys remember what does the graph look like? What's the horizontal asymptote? Because this is the graph as we go to infinity. What's the horizontal asymptote of a rational with the fraction, so with the top exponent being the same as the bottom exponent? Do you guys remember what the answer would be? What's the horizontal asymptote? Now, if you're not sure, let me give you examples. If I plug in 10, wouldn't that be 200 over 304? What if I plug in 100? That'd be 20,000 over 30,004. What if I plug in 1,000? That would be 2 million over 3,000,004. Well, what does that look like? It looks like it's getting closer to what number? 2 over 3. If you remember the rule from before, when I have the exponent on top and the bottom being exactly the same, what does the graph look like at infinity as we go toward the horizontal asymptote? It looks like the front coefficients. In this case, 2 over 3. So I wonder if you guys remember this rule. And that's why we needed to learn about what graphs look like, because we're going to be asked this question, what would it look like at infinity? Let's go and look at another one. So this is very similar. If I say limit as x approaches infinity of 3x to the 5th over 6x to the 7, no, 6x to the 5 plus 4x squared. If you remembered your rule about rational functions, if the exponents are the same, we just keep the front 3 over 6. That's what the graph will look like, which reduces to 1/2. And I'm going to actually graph this for you and to show you, prove this point that we're going to think smarter than harder. Come on, smarter than harder. We have a rule that we've talked about before. It's a 3x to the 5th. We're going to divide that by divided by 6x to the 5th plus 4x squared. Okay, if you look at this graph, you can see that we're stuck here. And what number are we getting closer to on the right? We're getting closer to 4.99999999999. Pretty much we're close to 5. This is a 5 with a decimal, but just round off error. Okay, it's just rounding up now. And isn't that what we said it was going to look like? Does it matter if it was positive infinity or negative infinity? Imagine if I said this was negative 300 over negative 600. Okay, wouldn't those still divide out to become positive 1 over 2? In this case, yeah, right? And that's because our rule about horizontal asymptotes for these basic type of fractions was nothing special. We had a rule, we can stick to that rule. So we are not really learning a new rule today. We're just reflecting on a rule that we learned before and applying it to limits, because I can tell you what it looks like now. Okay, let's give you guys another couple of these. What if I give you our third rule? So that's our first rule was, what if the bottom was bigger? Okay, bottom was bigger. We said we would go to 0 because if the bottom is running so much faster than the top, it buries the top. What if they're running at the same speed? 200 over 300, 20,000 over 30,000, 2 million over 3 million. Don't they just reduce to 2 over 3? Okay. And then the last one is, our third rule was, what if the top was bigger? 3, let's give it our limit as x approaches infinity of 3x squared over 5x plus 1. Okay. Now, in this case, I wonder if you guys remember the rule. If the top is bigger, we don't have a horizontal asymptote. In this case, we have a slanted asymptote. Sure, but does that slanted asymptote ever really stop? So you end up with a graph that, let's say, looks like this. Okay, it looks like this. I'm making this one up just as we're talking points, and this graph shoots off to what? Where is this guy going? Does he have a stop? If I draw an arrow going up from algebra 1, algebra 2, or pre-calculus, where is this number going? We're not getting stuck at a number like 1, 2, or 3. Every time I pick a number, the next step is higher. So this answer is infinity. There is no horizontal asymptote. What would it look like? What would it look like? How much money would be in my bank account as I shoot off to infinity? The answer, it would be positive infinity in this case. Now, let's see if that makes sense. If I throw a positive number here, isn't a positive times a positive a positive? Look at the bottom. What's a positive times a positive 5? Isn't that still positive? What's a positive? We have a positive infinity here. Oh, that looks terrible. Now, I want to talk about, though, because we're going to change this answer here to what is the limit as x approaches negative infinity of the same exact problem. Looking at this problem here, where do you think the graph is going to go? As x gets closer going this way, what happens to the y value, okay? Oh, sorry. These graphs are I made a mistake. Redraw this one. Sorry. Let's go this way. Okay. As x gets closer going toward negative infinity, look at the y value. It's getting lower, 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 lower. So my guess is it looks like it's going to be negative infinity. But is that true? Well, let's go ahead and test it. If I plug in a negative here, what's a negative times a negative? Because the square always makes it positive, we have a positive on top. But look at the bottom. If I plug in a negative on the bottom, isn't that 5 times a negative is negative? This leads us to say we're headed to negative infinity. I did not really do any math here. This is all really logic work. If a positive divided by a negative, that's going to be a negative. So no matter what numbers that come out of this, it will be a negative. Now let's go ahead and graph this on the right. I want to make sure that you guys can see that this wild and crazy bet, without me actually doing any work, is going to give us the answers that we were expecting. If you look at the graph, our values looking on the right, as x gets more positive, does it look like it's going to stop? It's going to shoot off to infinity. On the left, as I get more negative, more negative, more negative, more negative, more negative, more negative, it's going to exit on the negative side. It's going to become more negative. So what does the graph look like on the right? It looks like it's going to be positive infinity. What does it look like on the left? It's going to look like negative infinity. Great. Okay. How do we know that? We know, 1, there is no horizontal asymptote, so I'm not stuck to one number. 2, we see that this follows rule number 3, where we have a slanted asymptote. As x gets bigger, this is going to shoot off to the positive, and we tested it. If we put a positive infinity here, it's going to be positive over positive. So if we put a negative infinity, we ended up with a positive or a negative. And this tells us literally we are stuck being positive on the right, and we are stuck being negative on the left. So let's go ahead and look at your IXLs today. Whoops, where'd you go? Oops. So I got disconnected there. Okay, let's look at our rule before. So now, what about vertical asymptotes? Let's draw a vertical asymptote here. And let's say this is 1 over x minus 2, okay? The limit as x approaches 2 from the right, and then the limit as x approaches 2 from the left, 1 over x minus 2, okay? So can I do this problem? Can I do this problem without me having to graph it? Well, when I graph it, we know we have vertical asymptote at positive 2. Now, do you guys remember how I said we were on top or on bottom? Do you guys remember? Was there a fancy rule for it? No, I just told you plug in an easy number. If I could plug in an easy number like 3, if I plug in 3 and plug in 3, I want you guys to see what the difference, okay? Sorry, plug in 3. If I plug in 3, is that going to be positive or negative? Positive. What if I plug in 1? Plug in 1 here. 1 minus 2 is 1 over 1 minus 2 is negative 1. That's negative, right? And that's actually the same hint that we're going to do here, except I'm going to make it even easier than this, because all numbers might not be whole numbers, might not be nice numbers. Instead, this is what I want you to do. Pick a number that's super close to that number 2, okay? Because since we're trying to get to 2, pick a number that's close to 2. Now, instead of using 3 and 1, pick 1.99 on the left and 2.01 on the right. You might say, Mr. Ko, that's a lot of work. I get it's a lot of work, but I want you guys to look at this. 1.99 minus 2, 1 over 2.01 minus 2. I want you to notice about the sign. Please notice the sign. That's all you have to care about. Because we know at 2, it's going to be a vertical asymptote. We know it's going to be infinity, but is it going to be positive infinity or negative infinity? That's the part that we are unsure about. Is it going to be positive infinity or negative infinity? Now, I'm going to make this super easy for you, but please, you got to be careful. If 2 is my number I'm worried about, isn't 1.99 a little bit less than it? Look at this number. Is that going to be positive or negative? 1.99 minus 2. The limit as x approaches 2 from the left side of 1 over x minus 2. If I plugged in 1.99, because that's less than 2 on the left side of 2, does that look like positive or negative? It looks negative, doesn't it? Negative infinity. 1 over as x approaches 2 from the right side. 1 over x minus 2. Okay, darn it, this is limit. I don't know why I did that. Limit. What will it look like without me having to do all this crazy work about graphing? What will it look like, huh? So if I plug in 2.01, isn't that a number really close to 2 on the right side? Is this going to be positive or negative? 1.01 minus 2. It's positive. This would actually yield 1 over 0.01. That's a pretty big, that's like 10. No, that's 100. So this is going to be positive 100, positive infinity, because we're heading toward infinity. Now, using that skill, okay, let's do this one more time. The limit as x approaches 3 of 1 over x minus 3. And on the left, and limit as x goes to 3 from the right of 1 over x minus 3. I want you to tell me, is it going to be positive infinity or negative infinity? Please do not overthink this. This is it. We're trying to test the waters. You guys ever been to a swimming pool and it's summer, it's hot? What do you always still do? Don't you stick your foot in the water to test it to see what it feels like before you jump in? Even though you know it's going to feel good, you still test it. So give me a number that's less than less than 3. Isn't 2.99 there? And since it's less than 3, we're going to end up with a negative infinity because we're going to have more negatives there. If I put 3.01, because that's on the right side of 3, hey, isn't that bigger than 3? Going to be positive, positive infinity. And I can guarantee you that if I graph this on a graph, that's the direction that's going to head without me doing any extra work than that. Let's go ahead and look at the IXO real quick. Okay, so we're looking at what does the limit look like on the as we head toward infinity. Now, here's what I need you guys to make sure. You guys see that -8 is way over here? So what's a number on the right side and left side of this? A number on the left side would be -8.01 because it's more negative. A number on the right would be -7.99 because it's less negative than -8. So using that as a reference, would this be true? As we approach -8 from the left side, what number is on the left side? Left side is -8.01. Would this be more negative or more positive? I'm seeing -8.01 is bigger than 8, right? So with more negatives, bam, 1 over more negatives, it's going to stay negative. Would it be true that if I put -8 on the right side, 8.01, on the right side would be 7.99, -7.99. You can see that the 8 is bigger than a -7.9 because it's on the right side. So the reason why we use 7.99 is because that's on the right side, right? On the right side of negatives. Careful, that's always tricky. Kids always mess up on that because we go small negatives to large negatives on the left. Okay, so what does that look like? I see more positives. It's going to be whoops, this was the positive. I didn't even think about it. That was positive. So which one would it have been? So on the right side, since this would have actually been, this is the right side. The right side is not 8.01. It's 7.99. Sorry. So the answer is this guy here because we said then we're going to have more positive negatives. So we're going to be going up. Okay. Let's try it. I'm going to shoot off to positive infinity. See you later. Now, here is a tricky one. I see a squared. What does squared do to any problem? What does a square do to any problem? A square makes everything positive. So looking at this equation, even if I plug in a negative, so from the left side, 4.99 and 4.99 here. Sure, this would be a negative number, but doesn't a square make it positive? Everyone would have been positive. Over here, sure, it's going to be negative. Positive, 1 over a positive is still positive. So this was our answer over here. So once we plug in a number that's close to it, we then ask ourselves, hey, what would that number be? I don't need to know specifically what it is. I just need to know if it's positive or negative. Because if I try plugging in 5 here, we have vertical asymptote. Okay, if I plug in -9, we know that that's a vertical asymptote. So it's going to shoot off to infinity. -9, shoot off to infinity. But we're going to write this in a different way because we're getting to -9 from the right side of negative is -8.99. Careful, the 8.99 is on the right side. Here is -9, -8, -10. So 8.99, -8.99. That's on the right side of it. You want to say 9. We're so used to saying 9, but this is a negative. So on the right side of negative numbers are actually smaller, I guess, negative numbers, but they're really bigger negative numbers. And this would have been 9 minus 8.99 is positive. And if I 9th power, that's odd, a negative number, it stays negative. Wait, in this case, this is 9 minus -8.99 is positive. Positive to the positive exponent, sorry, to an odd exponent stays positive. It is not going to be positive here. If I put -8.99 here, we end up with more positive to the positive to an even exponent stays positive. Why is that? A positive times a positive times a positive times a positive times a positive. See, it doesn't matter if it's positive. The more positives we give, it's still going to be positives. If it's a negative, though, a negative times a negative is a positive. But a negative times negative times negative is then a negative. But a negative times negative is a negative times negative is a positive times positive is a positive. So it always depends on the number of negatives that you have. If we have an even number or an odd number, that is a key point. If it's odd, we stay negative, and if it's even, it becomes positive. So let's go ahead and run through these problems quickly. In this case, so we said if we plug in negative 8.99, this is still positive, stays positive. We are positive. So positive about that. If I look at 8 minus 8 is 0. We know we have vertical asymptote. But if I plug it in from the left side, so here is 8. From the left side is 7.99, right? 7.99, 7.99. If we have more negatives, this is negative to the cube power, stays negative, we are negative infinity. Okay, negative to the cube power stays negative. So we are, that's my answer. You guys have to be really good at these. You would save time. They're going to ask you these questions in college prep. This is a pre-calculus topic, so it is taught in calculus also. Okay, let's do this last one. What's going to happen? Here's my number line. Here's negative 2. And what's on the left side of negative 2? That's negative 2.01. Remember, it's more negative. I'm losing more money. So negative 2.01. More positive, more negatives? More negatives. So isn't the answer negative? But the even exponent, negative, 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 negative. So we all have negatives here. They're even pairs. It's going to be positive in the end. That's my answer. Because if you have an even set of negatives, it becomes a positive.